Hi, everyone, and welcome to Lecture 18 of ECE3311 Principles of Communication Systems. Today's an exciting day because we are going to be wrapping up very quickly the analog modulation schemes. And in this case, we're going to be looking at phase modulation, or PM, and frequency modulation, FM, right? So we kind of looked at all these different all these analog modulations over the last couple of weeks. In particular, what we've been looking at is things like, for instance, like amplitude modulation, right? We looked at DSB-SC, double sideband suppressed carrier. In lecture 17, we looked at single sideband modulation schemes, such as, like SSB. We looked at VSB, and we saw how we were able to implement these schemes using a variety of different types of formulations, including Hilbert transforms. So what we're going to look at, and we saw a little bit about this before, but we're going to go into a little bit more detail today, is the PM and FM modulation. So if you go to the course textbook, and I believe, let me double check because I don't want to give wrong information, is table 4.1. And survey says, yeah, I got it. All right. So table 4.1 is going to be kind of like an excellent way of looking at all the different types of schemes we've investigated over the last several weeks. So again, we go to sort of the core mappings, right? So if we have a message signal, M of t, okay, we have Gm of t. This is my baseband signal, okay? And this is a mapping of M of t. And then, of course, because I'm very sloppy in terms of terminology, V of t or S of t, they're the same, okay? And whenever I represent any of this, so in your course textbook, they use either, and in my notes that they use either. So just don't get confused, okay? Very important. This is passband. So very critical, very super duper critical. This is centered, okay, around 0 hertz. And this is centered at some carrier frequency that is not 0 hertz, right? Okay, so cool beans. So we got the bandpass signal, we got the passband signal. Now, let's look at the mathematical formulations we got here, right? So ultimately, S of t is equal to the real of G of M of t e to the j 2 pi fc of t. Awesome sauce. Now, this is where table 4-1 in your course textbook comes in useful, because it describes the different types of mapping that you can possibly use, okay, for creating AM, PM, FM, DSB, SSB, and all that jazz, right? So for the case of PM, it's very easy. G of M of t is literally, I just want to make sure the constant. So there's a constant, e to the j, dp m of t. And I'm going to show in a minute how it looks like as a phase. Then there's FM. Now, FM is a bit trickier because here, that mapping is JDF, also constant. So let's put constants. Constant. Now, this is different because now it's the running integral sum from minus infinity time to the current time instant of M of tau, right? So that message signal, as it goes from -infinity to now, we integrate all those values, okay, up until the present. So that's FM, and PM is just straight message into as the phase information. So the nice thing about the FM is it's kind of smoother. It smooths out because of that running integration. Whereas with respect to PM, it's kind of like value, 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 value. And so the phase kind of changes a little bit more quickly. We saw, as a side note, again, we saw quite a bit of stuff. So everything's kind of topsy-turvy. If I were to redesign the course, I would put these things up sooner. At the receiver, I would recover the phase information, the M of t, using something called the product detector. And then I would, for FM, this was very sneaky. At the receiver, I would use a variation of an analog phase lock loop. Okay? So cool. Awesome sauce. Okay. So now let's go back to the slides. So again, we come back to the same expression, right? Both for how we modulate in the time domain, what it looks like in the frequency domain in terms of the spectrum, and the power spectral densities with respect to between complex baseband and real passband. The reason why I call it complex baseband is because G of t can assume a complex value, right? But in passband, we can't have complex values. It's got to be all real, right? That's why we have the real operator. So now we go to phase modulation. We saw this. And we saw what theta t is equal to, right? So a couple of things. G of t sure as heck is not linear, right? It's an exponential function, and that M of t is driving it in the exponent. And theta t is directly proportional to M of t. Cool beans. Frequency modulation, on the other hand, here is, again, nonlinear G of t, because it's not only an exponential, but on top of it, we're like doing a running integral summation of the message signal. So here, theta t is directly proportional to the integral of M of t. Okay. So just as a FYI, from equation 2, what we got is the following. So what we have here is we have the spectrum is still going to look almost the same. It's going to be the same as if we had, like, you know, from equation 2, where G of f, okay, is going to be the Fourier transform. It's going to be the Fourier transform of G of t. Okay, so far so cool. And that in turn is going to be the Fourier transform of AC, so that's a constant, e to the j theta t. Okay, so that case, right, we got to be very mindful. Okay, what is the Fourier transform of complex exponential? Well, there's a Fourier transform table. So let's say if we look at that. So if you look for Fourier transform table, let me find it here in my computer. I have 2 computers, so thank goodness. Moo. All right. So there's a couple of Fourier transforms that you have to be careful of, right? So here, what you got to be careful about is exactly how that theta t operates on M of t. So the other thing is, what is M of t, right? So there's not like one size fits all Fourier transform here. Depending on what theta t is equal to, it will dictate how you solve that Fourier transform at the end of the day. All right. So if we work out the spectrum, so like for instance, right. So let's say we take, here we go. So let's say I bring up an example from a class test from many, many moons ago. Just trying to find it. It was a good one. Shucks, I thought I had a good one. All right, no loss. So like for instance, if we were trying to find a spectrum, so what would be a good message signal? So like for instance, so what would be a good theta t? So theta t is equal to dp m of t, right? So now what would m of t be? So for instance, like if we were to do the following. So let's say m of t, and recall that again, like g of t is equal to AC e to the j theta t, right? So let's say m of t is equal to minus a t squared. Let's say something like that. Let's say we have a signal that looks like that as you progressively go along. As just as a simple example, well, this one's going to be kind of easy to solve, right? Because what would happen is, let's say we have alpha. What would this? So let's say we plug in this thing. So therefore, g of m of t is going to look like what? So it's going to be equal to a c e to the j theta t, right? Replace that guy with let's say what that is. So it's going to be equal to minus dp alpha m of t alpha t squared, correct? All right. So now what we want to do is take the Fourier transform of that. So if let's say we want to find what g of f is equal to, we can take out AC, it's constant. And there's a reason why I chose this, because this Fourier transform is actually will yield the following. It's going to be, if you look at a Fourier transform table, this is going to yield right? Yep. That, right? So that's what spectrally this will look like if you do the Fourier transform of that. But that's, you know, in general, that's like I intentionally chose it just like eyeballing one of these charts. But in general, what you would do is, let's say if you have to do the Fourier transform. So what is the definition of the Fourier transform? The Fourier transform. Okay, let's just make sure I get the right. What this would be, and this would be from minus infinity to infinity, would be g of t e to the j 2 pi f of t dt, right? So to integrate that, and so what would end up happening is you would replace. So this is why this gets a little tricky, right? So what would end up happening okay, is, okay, now this could be very useful or it could be kind of disastrous. So what would happen is now you have this function here, right? You have, fortunately, you have a common base here. You have exponents. So you can combine these together if it helps, right? If it helps with respect to this minus infinity to infinity stuff, right? So very, very important. If this somehow helps with respect to solving for being able to simplify. In the case of like the Gaussian distribution that I just did there, that was kind of helpful because if you worked it out, and of course we could take this guy out because again, it's a constant. You would use one of, depending on what theta t is equal to, you could use one of several different types of integration operations in order to solve for what the integral of g of t is. Okay. Usually what I try and do is if it matches some sort of Fourier transform pair, I would do that. All right. And so like there's a number of ways that you can do this. Like for instance, I could I could take these two and then use Euler's relation and then break this up into a sine and cosine and integrate individually that way, right? Or if it's like, through proofs and stuff, this might be like a time shifted delta, but it really depends on what the value of that guy is, right? All right. So I do remember a good class test question. Sorry, folks, I'm just blanking right now. Where is it? Yeah, I can't seem to find it. Shucks. All right. So now let's move on with respect to the angle modulated signal spectra, right? So we saw this, and this is really important, but this is going to be a variety of different Fourier transform manipulations. My apologies for not having sort of a ready-made example that we could do together in order to solve this. But what would happen is, actually, I do, my mistake. Ha ha. Let's do this, shall we? I do have one. Here we go. So this is from class test 5. Wow. From 2019, so just last year, right? And this is from question 1C, right? And question 1C says, suppose I have S3, because there were several waveforms, 500 cosine, and here's 2 pi fc of t, plus 20 cosine 2 pi f1 of t, okay? And f1, oh, we already know that. Is equal to 1k hertz. D of f, oh, yep. Rads per volt seconds. So the question is, so we got that. Okay, awesome. So now what happens is we're going to try and ask, so we have this. So the question is, it's a reverse engineering question. Reverse engineer to get m of t. So what happens is this is actually kind of interesting. So m of t is equal to minus infinity to t. And then, silly. That's completely wrong. Yeah. df, yeah. Minus infinity to t. Yep. Correct. Is equal to 20 cosine. Correct. Okay. So the answer is, what m of t gives us that? Right? So this is kind of interesting because this is like if you had to engineer this in completely the opposite direction. So now, how do we do that? What we would do, okay, is like what would the integral of anything give us in terms of cosine? It would have to be a sine, right? So this thing is screaming sine somewhere. We are told what? df is 1 to the 6 rads per volt seconds. Okay. So we could go into an opposite direction in terms of like we could keep everything in volt seconds. So here, what is the equivalent of omega 1? Well, we know this is 1000 hertz, correct? And it would be over 2 pi. Nope. Silly me. Again. No, it would be 2 pi, 1000 hertz. Yeah, that's correct. Yep. All right, so we have that. We know in general, okay, that the integral of a sine, right, sine of t dt, tau d tau, what is that equal to? That's going to be equal to, let's see, that's going to be equal to minus cosine. Okay, t, right? And then there would be some constant. In this case, what happens is we have something slightly different because we actually have limits of integration. Okay, so what we would need to do in this case is the other way to go about it is if we had df, okay, minus infinity to t. I'm going to, no. That's what the solutions did, but I'm going to do that. And this, I did 1 correctamundo. So what I would do in order to get m of t, I would need to do 20 over df, correct, take the derivative of cosine. And again, what would that be equal to? That would be equal to that. We know that that's 1 times 10 to the 6. 2000 pi. Why? Because that is 1000 times 2 pi, because this was F1. Okay, cool beans. And then that would be sine 2000 t. Yeah, okay. And now what would happen is if we work out all the mathematics, what we would get is 0.1257 sine 2000 t. Okay? So that's a way where you use the definition in order to get that signal. And then what we would do is, all right, this is all cool. Let's take this a step further. So this would be equal to, right? This is just a phase term. This would be e to the j, right? 0.1257, not z, silly me, 7 sine 2000t. All right. And that is equal to g of t. Okay, correct. So now if I wanted to do, and this here, folks, is not in the solutions, right? But how would you go about it? So if I wanted to get g of f, I would need to take the Fourier transform, and that's the painful part. I would need to take the Fourier transform of this. And so that's the bad part. So how you take the Fourier transform of e to the minus j. So again, like first thing you would do is see if there's a reliable Fourier transform pair. Right? And if not, you're going to have to just go through brute force. Okay. So you would have to go through this. Yeah. And the thing is, it's going to be super duper not trivial, right? So you might have to pull some sort of like really weird integral calculus in order to solve that, which we won't do here. But like what you would do is, again, you would take the definition of the Fourier transform, right? And you would apply that. So this is what we're going to try and take the Fourier transform of. Okay. And then sine, bleh. And then this would be e to the j 2 pi, like f of t, right? And then it would be dt. So you would have to integrate this thing. So what you would get at the end of the day is, let's say if you combine the bases, is you would have this really complex time domain function that's brought to the eth power, and you would have to take the integral of that. Equivalently, what you could do is you could use Euler's relation and break this up into cosine and sine, so complex values. But now you have a cosine with a sine function in it, and vice versa. So this also would be potentially very tricky to implement as well, right? So that would be one way of doing that. Now, if we now go from here and we now do something like this. So right now what you witnessed was like, oh my God, that was crazy. How do I solve for that, right? So like, no, seriously. Like, let's say we go here, right? Like this Fourier transform is a little bit nuts, right? I'm going to be the first to admit it, because now you've got this like number, sine, and the sine is basically driving like, you know, complex exponential. If you have Euler's relation, right? So first of all, you combine the complex exponential. And then you have here, sine t. That looks like a t, right? And then dt, right? So you have that, right? And then it's like, well, if we used Euler, all this would be is this. Plus j sine And I would say, okay, have fun with that. So what we would do instead, magically, I would make an approximation. So remember, oh, I love this saying. So now is an appropriate time to use this saying. Engineers do for 10 cents what everyone else does for $1. If I can guarantee that that theta t, the absolute value of that is less than 0.2 rads, I can make a nice approximation. I can do this. I can linearize that complex exponential. That is fantastic. Oh, no, what? You don't believe me? No, seriously. Let's try it out with this like horrible, horrible, horrible expression here. So let's go back. What do I have? Theta t is equal to what? Is equal to minus 0.1257 sine 2000 t. Did I forget a j? Let me see. Nope, no j. Awesome sauce. So now I got that. And we saw what happens when we try and take the Fourier transform of that. Bad news, right? Don't like it. So what we do instead is we use that approximation. Does it hold? Does that approximation hold here? Is the absolute value of theta t less than 0.2 rad? And I lost track. Here we go. Does this hold? Not hold, apply. Yes. Thank goodness. Why? What's the min and max value of a sine? It goes from -1 to 1. Okay, great. Multiply by this thing, okay? The min and max is going to be 0.1257 to 1.1257. Awesome. So it most definitely is within the 0.2 rad boundaries. So therefore, what we can do is that g of t can be approximated, right? It can be approximated by the following expression. I'm always losing my space. Okay? Sorry, folks. I'm just like clicking all over the place. 1, I think it's plus j theta t. Fantastic. I can work with that. I can 100% work with that. Like seriously, like not even 100, like 1,000% work with that. Because and what happens is, how do we get that approximation? We got it from here, right? So we could approximate. Okay, so that's great. Wyglinski's note says it, but how did that come about? Because I could use Taylor series expansion. So I can approximate an e to the x by this expression if x is much smaller than 1. In this case, if x is, in this case, 0.2 rads or smaller, I'm in business. So that is actually super duper duper cool, because then what's the Fourier transform of this? First of all, what is the passband? Well, I would, again, apply this into my expression for the passband generation, and I would get equation 12. I'm all set. This is great. This is absolutely spectacular. So whenever you're working out a phase modulation or frequency modulation, I'm going to 100% emphasize, because what we get, if we go back to my problem here, remember I was trying to do the integral? This thing? How the heck do you solve? No. I already had the df. Silly me. boop, 0.1257 sine 2000 t. Like wowzers, okay? Now, because it's kosher, right? Because that thing is 0.2 rads, right? Oh, not per second. Because it's not that. I could approximate it by this. Minus. Okay. Ha! And then, first of all, what is the Fourier transform of that? Very easy. What do we know about that? That's going to be boop, boop, plus j, minus j. And it's going to be located at, if we look at omega or an F domain. So if it's F domain, it's going to be 2000. So 2000 divided by 2 pi. And here it's going to be plus 2000 divided by 2 pi. So we got that. Okay. So we know that right away. How about this guy? Delta F. It's fantastic. Wow. And then when we try and calculate S of t, okay, I'm been sloppy. G of t, G, M of t, same thing. Ha! So what do we know about this? That's a modulation. Then we take the real of all this. What we will find is it's going to look like equation 12. It's going to be modulation to FC and minus FC. It's fantastic. So that, folks, if there's a walk away from today's lecture, especially like if you saw how I was stumbling saying, how the heck do you take the Fourier transform of something that looks that insanely crazy? This is how. And that's only when right? You can make that approximation. This is super huge. Remember that. Like burn it into your memory. Okay. That is super huge. Okay. I feel pretty happy right now. All right. So remember that. Okay. So also with respect to communication systems, what ends up happening is when you have wideband frequency modulation, right? So what you can do is, again, you can translate this information using a voltage-controlled oscillator. Same thing we saw with the PLLs, right? Exactly the same thing as we saw with the PLLs in order to generate a WB-FM signal, right? And so in general, we don't want to do like these large fluctuations in frequency. Okay, it's not good. What we really want is a stable frequency source. So to do that here, like what you'll end up, there is a thing. Okay, we saw this a little bit before, called a frequency divider, right? And it's represented when we do, so a frequency divider. Right? And we saw this before where we had a block that looked like this. So frequency divider here, what we did is we divided the frequency by 2. So we actually used this a few lectures ago where we had like a double frequency term that we were extracting using a bandpass filter to remove the DC terms. And then we used the frequency divider to have its frequency, right? This is exactly the same thing where if we had a wideband FM signal and we wanted to make it narrowband, we would divide the frequency, in this case, by half, right? So that's how, looking at the questions that we have here in so far, you know, so like if we were to come up with another question, let's say phase modulation. And again, I'm going to do just one, I'm going to do a thing just off the top of my head. So let's say an example question. Okay. So suppose, you know, I'm doing phase modulation. And the phase modulation is dictated. So, and you'll see this, right, in things like phase lock loops and stuff. So suppose I have something like this, and the phase modulation consists of, like, you know, something really weird. Like, for instance, you have two sinusoids, right? So you have a cosine, and suppose it's like omega 1 of t, and then 1 times sine omega 2 of t. Shucks. Right? And so let's say that's 5. So if I have something like that, right? Like, imagine if you use definition, right? So by definition, g of t, which is equal to g m of t. So suppose that my message, again, is kind of boring. It's this thing here, right? So somewhere in there, this fella is dp m of t, right? And then the definition would say AC e to the j theta t AC e to the j, and then that would be equal to this thing here, cosine omega 1 t, and then 0.1 sine. Okay. Okay, that's cool. That's great. So now what happens is, first of all, one question would be, what is m of t? Okay, and the answer would be, all right, I have suppose that dp, okay, is equal to all right. Seems like I had a hiccup for a second there. Let's go back to sharing screen. All right. And then let's go back to the whiteboard. Hopefully it preserved. No. Shucks. The scribbles are not there. No, that's a bummer. So what ends up happening is, like what I was describing before, I had a theta t, and that was equal to what? That was equal to 5 cosine omega 1 t plus 0.1 sine omega 1 t. And suppose I say dp is equal to 20, right? So first of all, question would be, what's m of t? And then the second question could be a riddle. So let's say, for instance, I'm band limited. right? So let's say I'm band limited to, you name it. Let's say, give me a frequency. So let's say 10 megahertz. And at the same time, let's say omega 2 is 5 times as much as omega 1. The question would be, what is like, let's say omega 1 and omega 2? And then more importantly, draw G of F and S of F. So I'll leave that for all of you to solve, right? I'm going to save this because silly me didn't get a chance to save it. But with that, I think what I'm going to do is I'm going to leave it there. Again, the big walkaway from this lecture is equation 10. Very, very important, because this will enable you to actually visualize what these waveforms, like, be able to get the frequency responses without having a super duper big mess of a Fourier transform to take. Okay, so with that concludes lecture number 18. Is it 18? Wow, we are really zipping through. 18 of ECE3311 Principles of Communication Systems.